Here's a block diagram of how a compressor basically works. Usually the signal itself is used to determine how they affect the output of the signal. So if you've got a vocalist coming through a compressor and the vocalist gets loud, the circuit magically controls how loud it comes out of the amplifier, which is handy. Why people started thinking, well, we need a device that can control dynamics is because in the early days of recording, the devices were really sort of archaic and crude in terms of recording and capturing sound. The headroom in terms of how loud they could get before it would distort was very small range. The electronic range that it could capture before it went to distortion, or how quiet you could get before it wouldn't record it properly, was because it would be too quiet to record it well. It was very much limited to a certain range of loudnesses. And that's why they started thinking, well, gee, if we had something that could put it in that automatically, put it in that range, then we wouldn't have any problems. We wouldn't have any overloading distortion. We wouldn't have any spots where it was so quiet we couldn't record it, that kind of thing. So that's how they started thinking, well, if we could design something that would do that, and they did. And inadvertently, they created something that's extremely important to recording arts. And I'll get into it fully because there's so many ways to look at what a compressor does. Not only controls volume, but it does so much more. Okay, compressors reduce or compress the dynamic range of the input and leaves the signal below the threshold. There's a threshold at which it starts operating. So if it gets louder than the threshold, it starts operating. And when it starts operating, it slows down how loud the signal gets above the threshold. You can set at what point you want it to start limiting the dynamics. So if you set the threshold really high and the signal never gets louder than that, it's not going to even operate on the signal. If you set it lower, then it's going to start operating on the signal. Our ears compress. So when you hear a loud sound, we know enough about our ears to know that the human body protects our hearing. What does it do? When a loud sound comes to our ear canal is a muscle, closes down to limit how much sound gets to our eardrums so our eardrums don't bleed. So what is that? That's a limiting of dynamics. That's a control of volume to our ears. And actually, I would even propose to say that anything compressed sounds better. So that's why I love compression, because it makes everything sound great. But it also has the effect, since we know about spectrums, let's talk about the spectrum of the sound that's coming to your ear as your ear is closing down and not letting as much volume to the eardrum. What happens is the fundamental frequency is the frequency that's the loudest in a sound, right? We just discussed that. So the loudest frequency gets limited, and what happens to the perspective between the loudest frequency and the harmonics? As you start limiting the volume of a sound, basically what happens is the loudest frequency comes down in perspective to the upper frequencies. So what does that do? That means that the frequency, which is the fundamental that carries the pitch information, gets quieter in perspective to the other frequencies that carry the quality of the sound. So that means your ear can hear more of the quality of the sound at a louder level because the fundamental frequencies being limited. What does that do? That means that you hear more frequencies that represent the quality of the sound. So a cymbal sounds more like a cymbal. A human voice sounds more like a human voice. A piano sounds more like a piano because you're hearing the upper harmonic structure louder in perspective to the fundamental. So what I'm saying is it readjusts the frequency dynamics of what sounds are in the spectrum, or what frequencies are in the spectrum, to be more precise. And if you think about it, when that happens, we actually hear things and our brain perceives it more like the sound that we think we're hearing. Does that make sense? Everybody buying that? You don't buy that? Okay. So when we limit dynamics, the fundamental frequency in a spectrum is the loudest frequency. So when we limit that, the balance between the fundamental frequency and the harmonic structure changes from this being the fundamental being much louder than the harmonic structure as it goes up in frequency to this, where the fundamental is quieter in perspective to the harmonic structure. Therefore, we perceive more harmonic structure in general. Now, if it was one sound, one dynamic, we could take an EQ and add higher frequencies to the sound and hear more of the upper spectrum of the sound. But it's not. We're listening to sounds that are dynamic, constantly changing. And when they change, that means they get louder and quieter and louder and quieter, and they have different frequencies in them. So adding an EQ that statically adds high frequency means that when a sound is quiet and when it's loud, we're adding the same amount of additional frequencies to the spectrum, or additional volume to certain frequencies of the spectrum. I'm trying to show you the difference between something that's dynamic and something that's not dynamic. A good example, and I might be getting ahead of myself, but a good example of this is when somebody plays a piano chord quiet or they play it loud, right? You hit it hard, you hit it soft. When you hit it soft, you resonate the strings, you have a certain amount of energy that's resonating inside the cavity of the piano, and then it dies away. When you hit it hard, you're adding more energy, which means that it's going to resonate more, longer, different frequency, different spectrum actually is created. Fundamental frequency may be the same if you hit the same note, quiet and loud, but the harmonic structure changes from playing it loud or quiet. As you hear, the sound actually changes. And I think we can all agree that when you hit it soft or hit it loud or hit it hard, the sound changes. So what happens is the harmonic structure changes with the added energy of hitting it harder. So if we just add an EQ and add high frequency, when we hit it soft, it may sound perfect, but when we hit it hard, it may have too much high frequency in it. So it doesn't adjust or compensate for the fact that I'm playing it dynamically and that the spectrum's changing. We haven't talked about EQs yet, but in general, in my world, I use a compressor first to limit dynamics, and then an EQ to fine-tune what frequencies I want to hear in that sound, because I'm not going to fight the dynamic then. So I'm not fighting the changing spectrum of the dynamic. If I put the EQ first, I'm constantly battling the spectrum change, and then I'm compressing it and balancing it in terms of dynamic. I think that compression actually corrects the sound in a better way, in a dynamic way. Because when you hit a snare drum, right, and it has a ring in it that you don't like, let's just say, right, and you hit it soft, the ring doesn't last as long. It's not as resonant at that frequency. When you hit it hard, that's when the ping comes out of the snare drum too much. And you could take an EQ and you could try to nail that frequency down and reduce it so that it's not so aggressive. But what happens when he plays quiet? Then you're reducing that frequency the same amount. So if you control the dynamics first, then it's going to be more consistent, and then your EQ is going to be more consistent from when he plays it loud or quiet. Even my voice has so much dynamics that I can overload a microphone if I get excited and I'm talking about, oh, I love compression, it'll start really overloading the equipment. And so for the very reason of controlling dynamics so that your equipment records properly. Now that's not used to alter the sound as much as it is used to make sure your equipment can capture the sound. So as I said, compression is used in a multitude of ways, and it's all good. That's why I love it. So just in the fact that you're using a compressor to make sure your equipment records properly. For example, with Pro Tools, digital recordings, if you go over the limit and you go past the top, it'll just clip and start sounding horrible. If you get too quiet, it's not going to have a lot of bit depth to get much definition. So you really want to have the dynamic be sort of controlled, a lot more actually than tape. Tape is more forgiving when you go over into the red, so to speak. I think everybody agrees that loud music sounds better. That's why, right? You're able to hear more high frequencies because you can get it louder, and in the cochlea, it can actually go deeper into the cochlea, right? For the low frequencies, you hear more of the, and you remember that diagram that I showed of the ear and its spectrum, its frequency response? If you look at that curve again, when the music gets louder, it gets flatter. It gets flatter because we're dynamically compressing it, so the music gets louder, it can hit further into the cochlea, which is that sort of spiral thing in your inner ear, right? So you hear a flatter frequency response at louder music. So you get to hear high frequencies and low frequencies better than at quieter. Isn't that spectacular? It's a dynamic equalizer, and I'm getting there. You're ahead of the curve here for a second. But yes, that's exactly what happens. If you want to think in terms of equalizing. I mean, I've sort of abandoned that ship a long time ago. I think that everything's about compression. And I'll tell you why. So when he was in the video showing, how he was manually adjusting the level to keep it the same, he was moving extremely slowly. He was moving at a snail's speed, and he's a human. So he can only perceive and then move and try to compensate for level changes. Whereas electronics can be very instantaneous. They can be very fast, much more instantaneous. So when you do this slow movement, you're really just adjusting level. But let's think of the example where you've got a snare drum, and think in the time domain for 1 second instead of the frequency domain. I already explained what happens in the frequency domain. In the frequency domain, if you compress, you push down the fundamental and the harmonic structure comes up, so you hear more high frequencies and more. It makes it sound more like what it's supposed to sound like. So let's just look at it in the time domain for 1 second. You've got an envelope of a snare drum being hit or a piano being hit, where you've got an attack, a decay, a sustain, and then a release. What happens if you set up your compressor so that it's fast enough that when the attack happens, it goes, wait a minute, you're getting too loud, and it changes and pulls down the attack of the envelope because it's fast enough, not just a human being pulling it down where it hears the attack and about 3 milliseconds pulls it down, but when it happens almost in real time. So it basically sees an attack, it goes over the threshold and reshapes the attack, and then holds on to it and reshapes the sustain and the decay and the release. What is it doing? It's reshaping the envelope of a sound based upon a dynamic range where you set the compressor threshold, where it starts happening, and how much it shapes it. So you're shaping the time domain of a sound, right? The time domain spectrum, the time domain envelope of a sound, and what ends up happening is when you change the envelope of a sound, you change the spectrum. They're interlinked. They're two descriptions of the same event. So if you change the envelope of the sound, you're changing the spectrum. So now I'm describing what happens with compression from the envelope perspective, whereas the spectrum perspective is we're pushing the fundamental down and raising the harmonic structure. From the envelope perspective, we're reshaping the envelope. And by reshaping it, we can precisely change what frequencies, how loud they are in the sound. So that answers the question, what is it really? Well, it's a dynamic EQ because it changes the amplitude of different frequencies in the sound based upon how loud the sound is. Right? So if it gets louder, it changes it more. If it gets quieter, it changes it less. It's a pretty cool device. And they didn't know that they were inventing this when they were just trying to control levels and volumes.